Hello fellow problem solvers. So today we're going to be doing a problem from the Junior Balkan Math Olympiad from the year 2002, problem number 3. I suggest you try this nice number theory problem out. It's very nice, especially if you want to work on the divisibility skills. It doesn't really help to know any specific technique very well. It's really going to test your thinking and problem solving abilities more so than is technique. So, and here I invite you, especially if you're a junior level, on that sort of level with number theory, this is a great problem to push you forward to the next level. And I invite you to try it out for a minimum of 25 minutes, ideally 45 to an hour and 15 minutes, maybe even an hour and a half, though not more than 2.5 hours. If you'd like to go along with us, give this a go for the next 5 minutes. Just put your first ideas out on paper. And now let's begin. So we have this integer n has these divisors d1 through d16. So these are all its divisors, right? And we have that, we must find n such that it has these 16 divisors. It's all of them. These are all its divisors, and this holds true. Now, what is the first sort of thing that we know about n given this is true? And the answer is, well, we know this number, d of d5. This number has to be between 1 and 16, right? Because dd5 is a divisor for this equation to make sense. And so we know that d5 is less than or equal to 16. And that's sort of the first thing we know. What else do we know? Well, actually I invite you to pause for a minute and ask yourself, what else do we know? And the answer is, well, we know also that d5 is going to be greater than or equal to 5. However, it needs to be greater than or equal to 6. And now we can't really say that much more about d5. Or can we? Well, we know d2 is going to be a prime divisor. Right. It's going to be the smallest prime divisor. Now, what is d3 going to be? Well, it's either going to be p squared, or it's going to be the next prime divisor, 2 or p1 squared. And then d4 is either going to be, actually, how many prime divisors does n have? Maybe is a question we could ask ourselves. And I invite you, maybe looking at this a bit, to pause for 3 to 5 minutes, or even 10, and ask yourself, what would you do next here? And for me, what I would do here is say, wait, it has 16 divisors in total. How do I calculate the number of divisors a number has? And the answer is, well, if n, any number, is of the form p1 to the alpha 1 times p2 to the alpha 2 times pk to the alpha k, then n has a total of how many divisors? And the answer is, it has, this is a formula on one hand, but I also want to show to you here, if you haven't seen it, how you would come up with this is pn. You can take all the how many divisors does this have? It has some number of divisors. And then n has the number of divisors this thing has, plus for every single one of these divisors, we're going to multiply by 1, by p1 squared, all the way till by p1 to the alpha 1. So in fact, n has the number of divisors this number has times alpha plus 1. And then if you take this number out, you'll get the amount of divisors starting from p3 to the alpha 3, how much this number has, times alpha 2 plus 1. And then via that, thinking about it, if you just had pk to the alpha k, you would have numbers 1 through pk to the alpha k, which would give you alpha k plus 1 divisors. So n has alpha 1 plus 1 times alpha 2 plus 1, all the way till alpha k plus 1 divisors. Now we have this number is equal to 16, right? And every single one of these is at least 2. So we have this is equal to 16 for our n. Now what does that tell us? Well, mind you, every single one of these numbers is at least 2. So this is greater than or equal to 2 to the k. Because we have 2 times 2 times 2k times. Which means k is less than or equal to, because this is 2 to the power of 4, is less than or equal to 4. So n can have at most 4 different prime factors. So n is of the form p1 times p2 times p3 times p4. That's one way we could get it, 2 times 2 times 2. Another way we could get n is if one of them was 4 times 2 times 2, then we'd have n is, say, p1 squared. Here I'm not ordering p1, p2 another way. Actually, though, if it was 4 here, we have p1 cubed, p2, p3. We could have it as 4 times 4, so that would be n is equal to p1 cubed, p2 cubed. We could have it as 8 times 2. And I think that's just, so we could have it be n is p1 to the power of 7 times p2. So n is one of these forms, right? That's what we know. Okay. Now the next part is here. If you actually haven't figured this out, I invite you to pause for another 5 to 10 minutes and see what else would you do here. And here's my response. Now, I would be looking at what these divisors, these things tell me. I have d5 is less than or equal to 16. I'm still kind of not sure what d5 could be, but I think I'm pretty decently sure that given d5 can't be greater than 16 if n is of this form. Then it's like the first, say p1 is less than p2 is less than p3 is less than p4 in this case. If n was of that form, I'm going to have like my smallest, what's called divisors are going to be p1, p2, p1 times p2 maybe, in a few cases. And then p3 and p4, to get 5, to have, like I would need to have p3 to be less than or equal to 16, perhaps, like less than or equal to 16, to have something sensible here, right? So I'm getting some sort of bound. I think this falls off pretty quickly because the smallest number the smallest sort of divisors it can give us is we could have here, if this was 2 to the 7th times 3, then we have the divisors are 1, 2, 4, actually a 3 before that, a 6. Actually, so we could deal with this. I thought for a second we couldn't deal with this. If we had to deal with this, the smallest one would have to be 2 perhaps, right? If it was a 3, we would have 1, 3, I'd say this was a 2, 2, 6, 9. We're still in the clear. With 5, we would get out of the clear, but it's a tricky thing that I'm still not getting d5. I'm still not getting this estimate without going into too much detail about what these primes are. I could perhaps say what maybe the smallest one of these primes needs to be, or the second smallest one, or the third one, but I'm still not there yet. So what do I do? Well, let me go back to the drawing board. Let's see. There's also a hint in a year if is 2002 the answer because this is the JBMO 2002? Maybe, and this number is even. But beside that, because that's almost like a cheat code, is you want to say, wait a second, let me look at maybe what's my smallest prime divisor, because that can sort of determine how the other ones behave. And here, I can also figure out D2. Now, what if the smallest prime divisor was odd? In other words, what if n was odd? What would happen then? I invite you to pause for 3 minutes, just think about that. And the answer is, well, if n was odd, then every single one of its divisors would be odd. And then we'd have d of an odd, this would be odd, this would be odd, this would be odd and odd. When you add them together, you'd get an even. You'd get this side is even, this side is odd, a contradiction. And so for the first thing we sort of see here now, I mean, not the first thing, but one of the first things we see is that 2 is divisible by n is divisible by 2, which means that d2 is in fact equal to 2. And now it's getting a bit more interesting. What do we know about, say, the next one? If n was of the form, can it be of the form of square? No. So we could have n have a cube or to the power of 7th. We know its smallest divisor is 2. What is d3 going to be? What are the possibilities? Well, d3 can be either 2 squared, and if it's 2 squared, n is one of these numbers, or it could be p, the next prime number. So if it's the next prime number, if it's p, then we can look at those as 2 separate cases. What happens if it's a 2? What happens if it's a 4? What happens if it's a p? Let's start maybe with the case what happens if it's a 4. If it's a 4, then we know 3 doesn't divide n. Does that give us any contradiction? Say this is now 2 plus d4. d4 could be any, we can make this a prime number such that this isn't divisible. Like, the only question is, like, will this mess us up right now? And also, mind you, this is kind of wacky that this holds true, right? d6 times, also we know d1 times d16 is n. d2 times d15 is n. And so d6 times d10, d11 is also equal to n. These are sort of like going to be smaller-ish, and this one's going to be bigger-ish. And it also makes sense it's going to be bigger. Maybe with 2 divides n, we can get something about d5. So maybe now I really want to get over like the cases where, say the next one actually is a 4. So say d3 is equal to 4. I'm looking at this because I want to get rid of these cases where I'll have 2 to the 3rd, to the 4th, to the whatever. Say d3 is equal to 4. Then n is divisible by 8. Then we know this to be a fact. We know n to be divisible by 8 because it's either of this form or it's of this form. Right, if a square divides it, then either 3rd or 7th power of 2 divides n. And now we have 8 divides 8. So we have the numbers 1, we have 2, we have a 4. Say d3 is now 4. We're going to have an 8 as well. Now we're going to need to have a prime divisor somewhere here. And now we can look at some cases. For example, this is d2 plus d4. If 8 is equal to d4, then we have this side is divisible by 5. So if these were if the next prime divisor was bigger than 8, if it was at least 11, we'd have this is d4, this is d2, and then we get this thing is divisible by 5. We get a prime divisor is divisible by 5, which means n itself must be divisible by 5. But that is not the case. So if we have a 4, if 4 divides n, then we know then 8 divides n. Now d3, that doesn't necessarily need to be 4 at this point, though. Let's just say that 4 divides n is this case. Then we know that we need to have a prime between 4 and 8. And that can be one of 3, 5, or 7. And now maybe, let's look at those cases. Let's see what happens if we pick a 3, if 3 divides n. Well, then we will have 1, 2, 3. We'll have 4, and we'll have a 6. This is going to be, d5 is either going to be 6 or 5. But now we have 2 plus 4 is d2 plus d4. We're going to have 6d6 divides this, which is like this thing divides n. I have to actually just write this down. This divides n. And so I have n is divisible by 6. Could it be divisible by 5 as well? Maybe. So we either have, so let's actually look at, again, cases. Let's say the next prime was not equal to 5. Then we would have this number right here. What if it's a 7? Actually, no, we'd have d5 is equal to d6, which is which is impossible. This has to be bigger than d6. So maybe that's a thing we need to look at. So if we have 1, 2, 4, 8, we need d5 to be bigger than d6. Or, like, d5 needs to be bigger than 6. In other words, this side will be bigger than this one. So we're doing this bounding as well. This is why I think this is a very, very good practice problem. Like, if you're really, like, I'm not using any heavy theory here. I'm just looking at these cases and I'm building up an understanding of what it is that's happening here. That's why I really, really urge you, and I urged you before, to go ahead and try this problem. So now let's try to bring this together, this whole sort of idea. If 4 divides n, 8 divides n, and then I have divisors 1, 2, 4, and 8. Right? If 3 divides n, I'll get a contradiction. Right? I'll get d5 needs to be greater than or equal to 7. And what I'll get is, what's it called? I'll get a 2. Though even maybe a 7 is a weak estimate. Because mind you, this is d6 times d2 plus d6 times d4. It seems pretty plausible that this should almost like additive, that this should be around d10 or something like that. Like, that's sort of what it feels like. I can't prove it right now, but I'm getting a feeling, and it's important to develop these feelings. They could be wrong, they could not. You're developing feelings for problems because they can nudge you. I'm going to do this, I'm going to do that. They can give you hints as to what you need to try and prove. But now we're looking at this case. Let me stop blabbling and start going on, start trying to solve the problem. I have these 4 numbers. I have the prime number can't be equal to 3. If 5 divides n, let's look at this in cases. First case, 5 divides n. Then I have 1, 2, 4, 5. I have an 8. And now this side becomes d2 plus d4 becomes 7. So that implies that 7 divides n. So I have 5 and 7 divide n. What does this tell me? This tells me n has 3 factors. So n is of this form. Right? We're also using what we had before. So n needs to be of the form 2 cubed times 5 times 7, if this is the case. And then we need to check this out quickly. We have d6 is 8. We have 8 times 7 is equal to d5 is 7 is equal to d7. And this just does not feel like the case. 8 times 7 is one of its biggest divisors, whereas d7 is in the lower half of its divisors. This is just roughly how I'm doing this in my head to double check. But we can check this and figure out that this actually doesn't work. So we have the second case where 7 divides n. And we have the non-divisors are 1, 2, 4, 7, and 8. Now if I add a 7 and a 2, I'll get 3 divides n, a contradiction, because I assumed 7 was the smallest prime divisor. So this seems like 4 cannot divide n. And as we said before, if a higher prime number divides n, then we'll have 2 plus 8 is divisible by 5. A contradiction that we didn't have a smaller prime number that divided n. So we have 2 divides n, 2 divides n. This also implies that 4 does not divide n. And there's also a way to write this down. It's like 2 to the first fully divides n. And it means 2 divides n and 2 to 2 to the first divides n, 2 to the first plus 1, 2 to the 1 plus 1, which is 4, doesn't divide n. And now we have this. So we've shown that n is divisible by 2, and fully divisible by 2. And now we know that d3 is actually equal to p2. And then d4 is going to equal what? Well, either one of two things, either p3 or p2 times 2. And here's where I'm going to invite you to pause for the next 10 to 15 minutes, try to push the problem further while I will clear out the board. Now, I don't know about you, but I feel very, very nice about this problem. It might feel a bit, I'm just like trying out a bunch of cases, but for me, it feels like I'm also thinking about how it is I'm going to approach this, a better estimate, a worse estimate, and stuff like that. So I feel very good about the problem. Now, we've said previously, n is either of the form p1, p2, p3, p4, or it's equal to p1 cubed times p2 cubed, or it's equal to form p1 cubed, p2, p3, or it's equal to p1 to the 7th, p2. There's also a case it's equal to p1 to the 15th, but that is now not possible because we know that 2 needs to divide n and 4 does not divide n. So we know these things. And so we know its prime factors are going to be there. Like it could still be these two types of numbers. It could be 2 times p to the 7th. It's possible. It could be 2 times, a 2 could be here. Though actually we know it's not this form anymore because 4 doesn't divide n. So we know it's of either one of these 3 forms. But now we're going to say, okay, d3 is going to be equal to the next prime factor, and then d4 is either going to be equal to 2 times the prime factor, or it's going to be equal to the next prime factor q. And if it's of this form, we're going to get it's equal to this. I think we should be able to actually quickly rule this out right now. Because if it's of this form, we'll have the factors are, so it's 1, 2p, then it's 2p, then it's p squared, then 2p squared, then p cubed, then 2p cubed. Now I have the 1, 2, 3, 4, 5. I have d5 is equal to p squared, which needs to be less than or equal to 16. This just only means p can only be equal to 3. And now I think we will rule this out quickly. So we have then we have what n is, and what we get here, we get actually d2 plus d4 becomes 2 times 2 plus 2p, which is going to be equal to 2 plus 6. This side is divisible by 8. N is not. Maybe there's something about factors of 2 now. New idea just came to me now when I saw this. But this is going to rule out this case actually immediately. If we just say, then we're going to have 2p. This is going to be d2. This is going to be d4. And then d2 plus d4 is going to be 2 times p plus 1. And then this is divisible by 4. And that's a contradiction because we've shown 4 does not divide n. So we know that n isn't going to be of this form. Now, can it be of this form? Probably we don't know yet. Or can it be of this form? Like, these are things we still do not know. But this has actually prompted an interest for me as to whether or not we can go and say, this is going to be what? 2 plus, if it's going to be 2 plus 2p, right? If it's going to be this, in this case, we're going to have 2 times p plus 1. And then this is even. And then what does that mean? And then this is divisible by 4. Well, we said n cannot be divisible by 4. So, this means this isn't the case. It means the form needs to be a prime factor. Now that's, I think, for me personally, that's a bit cool. I mean, it's kind of cool to me at least. So this is a prime factor then. And we can have this be 2 times p. And that's not going to change anything, but we know d4 is now going to be a prime factor. So now we know n has at least two different prime factors, right? Because this can't be p squared because 2p would be smaller than p squared. And it has at least 3 prime factors, so it can still be either this or this. Now let's see what we have. We have q plus 2 times d6 divides n. We're also looking whether d5, so it's either now going to be one of a couple of things. It's either going to be 2p or a factor r, a new prime factor r, because no other combination is smaller. Right? This is the smallest possible thing we can have. 2p is smaller than p squared, so it's one of these two. And now, mind you, actually, if it's 2p, is that plausible? Right? If it's 2p, it says that, mind you, this has to be less than or equal to 16. So if it's equal to 2 times p, then we're going to have that prime factor p here is less than or equal to 8. In other words, it's either 3, 5, or 7. Those are a couple of cases we can check them out, even by hand. And it wouldn't be too much of a fuss. In the case that it's r, that can also work. It just needs to be a prime factor less than or equal to 16. So it's either 3, 5, 7, 11, or 13. That's about 5 cases, right? And from there, it's also doable somewhat by hand. It's not the best thing, but we might be able to also figure something out. Something different, something outside of that. So maybe we can get rid of this case by assuming it's r. Let's say it's r. What would that mean? Like if we have d5 is 2p, I might be even inclined to go on a case-by-case basis, just finish the problem. But say it's equal to, or which case actually is easier? Is 2p easier or is r easier? And then I have d6. Maybe d6 is also something cool. It's either one of these or it's going to be equal to 2 times q. But we have also, here's the thing, we have q plus 2, where q is the second, what's it called? Actually, let's say n is of this form. Let's say n is of this form. Let's say it has these 3 prime divisors. It's not r, it's 2p. Now, this number right here is odd. It has prime divisors. This number right here, so because it's odd, because q is the biggest prime divisor of n, by this thing right here, by our ordering, q plus 2 cannot be prime, but it is odd. And it does divide n. So this means that q plus 2 is in fact needs to be divisible by the prime factor p. So p needs to divide this. Right, it's the only other odd prime factor. Furthermore, this q plus 2 cannot have any other odd prime factor. It doesn't have q. So q plus 2 is either going to be some p squared or p cubed. And that's, if you think about it, that's this case right here. So if n is of this form, then n is of the form 2 times p cubed times q, where q is greater than p. And that is what happens. And if this is the case, also, like if this is the case, actually, if it's the case that n is of this form, then we know this is the case. And from there, given this, no, not even given this. From there, we just know this means that n is of this form. Now, what do we know about d6? Well, d6 is either so p squared is going to be greater than or equal to q plus 2. But q plus 2 is either p squared, actually no, it's less than or equal to q plus 2. Because q plus 2 is either p squared or it's equal to p cubed. Maybe both of those are impossible given some remainders of some prime numbers. But I think that this is a perfectly fine thing to look at. And maybe p squared is equal to q plus 2. And now we know not only this, but we know q is equal to either p squared minus 2 or q is equal to p cubed minus 2. Yeah, I think this is actually incredible that we have this. Now what about d6? So we've had d5 is equal to 2p, and then d6, so it's not going, because it's of this form, what is the next smallest one? Is p squared smaller, or is q smaller? Or is actually 2 times q smaller? Well, by this thing right here, p squared is smaller than q times 2. P squared is less than or equal to this. And this thing is going to be greater than 2 times q. So then d6 is equal to, I wrote that out already, is equal to p squared. But then we're going to have a contradiction. Then we're going to have p to the power of 4 is what we have on this side of the problem. And p to the power of 4 divides n. However, that is not what we've seen before. So this cannot be the case. And now we know that n isn't going to be of this form. And we know, in fact, n just is composed of 4 different prime divisors. It's composed of 4 different primes. The first one of which is 2. And now we can actually, look at these cases, whether it's 2p or p. But we still need to look at this. This q plus 2 is still going to be the smallest one. I'm trying to remember, yeah, 2p wasn't because we had 2 times p plus 1. So q plus 2 is going to be odd. d5 is going to be either 2p or r. Okay, what can we do now? Well, we can go ahead and look, okay, this q plus 2 is either going to be p squared, though actually it can also be 2 times p. I didn't actually check that out here. I should actually check this out. Can q plus 2 be equal to 2p? And the answer is, oh yes, it can't, because if q plus 2 was equal to 2p, that means q would be greater than 2p. No, actually, wait. Would q be greater than 2p? No, q would be then less than 2p. Q would be less than 2p if q plus 2. That's also a thing actually we need to check out in this case. If q plus 2 is equal to 2p, if I'm not horribly wrong, so I have then 2p. Now q plus 2 is equal to 2p. Then I have, this is d5. And then what is up with d6? Oh, actually, no, this can't be equal to 2p because q is odd. My bad, I don't need to check that out. But now I definitely have n is of this form. And here again, this is sort of a part where I would invite you to go ahead and pause for the next 10 minutes while I'll clear up the board and write down what we have. We have this. We have that d3 is p, d4 is q, which means also q is less than 2p, is greater than p. And with that, let me clear up the board. So now what we have is this situation. And remember, our original equation here gave us d2 plus d4 now times d6. We know is going to be equal to 2 plus q. 2 plus q times d6, which is either going to be 2p, r, or 2q. It's going to be one of those, things. And it's like on a case-by-case analysis, if it's r, we know it's equal to 2p. Maybe that can give us a hint as to what it is. But we know this number right here, this divides n, 2 plus q. So given 2 plus q divides n, what can we say about this number? It's either equal to r, the next prime number, the prime number r, or it can be equal to 2 times p. However, it's not equal to 2 times p because it's odd. So 2 plus q is in fact equal to r, our final prime factor. And now the question is, we know that q is less than 2p, it's greater than p, just by virtue of this. And now we know that q plus 2 is equal to r. Right? That is what we know now. And this is how it's like, this is why, again, one of the many reasons I like the problem is because, this sort of thinking, boom, 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 back and forth. And also, mind you, this means q and r are consecutive primes. And mind you, what we also have for r. Mind you, if 2p, we have d5 is less than or equal to 16. Now, if r was, we know q is smaller than both r and 2p. So 16, d5 is strictly greater than d4, which is equal to q. So now we know that q and r are prime factors such that there is a smaller prime factor than them, but q and r are two primes which differ by 2. And q is less than or equal to, actually strictly less than 16. So now what does this tell you? Please pause for the next 5 minutes and try to push this problem further now. And the answer is, well, this part tells you that q, like what are the primes that we have? We have 5 and 7. Those differ by 2. There's a 3 below them. And we have 11 and 13. Those differ by 2. But you can't have 3 and 5 because you need a prime number that's between q and 2. So the small one can't be, q can't be 3, so it needs to be either 5 or 11, which also constrains p to either be 3 or it's equal to 3, 5, 7. Now we could even maybe get away with a couple of case-by-case things, or even look at what does this mean for us in terms of this equation, like this times this is equal to this. So now we know this is equal to r, and the question really is, actually, to be very frank, d5 isn't going to equal r. In which case? Well, in the case that 2 times p is equal to q plus 1. If q plus 1 is equal to 2p, then we have that this number right here is going to not be r. In fact, it's going to be 2p. And then we definitely know this is equal to r. But in fact, we know also this now cannot be q. It can't be 2 times q. If this is 2p, this is definitely r. So we have a lot of things here at hand. Now, one thing we could do is just say, okay, let's do case by case. Let's say this is q, this is r, then p needs to be 3. And let's see what it is we have. We have the prime divisors are 1, 2, 3, 5, 7. The 4, 5, and 7, I get a 6 here. That's that thing right there where the 2 times, 2 times p squeezes in between q and r. And I have 2, 3, 5, 6, 7, d1, d2, d3. So I have 2 plus d4 is 5, 7 times d6 is 7. Oopsie doopsie. We have 7 squared. So this falls right out. And it means that Q and R are going to be 11 and 13. So now we have the prime, the factors are, we're going to have the divisors actually going to be 1, 2, P, 11. And now if it's, the only thing that can be between 11 and 13 is 12. Right, we know that 2 times P is, actually we also know this. So 2 times P is greater than R, so P can't be equal to 5. So P needs to be equal to 7. So 2, 7, 11, 13. And now we're done. Now we're done. We just need to now double check everything because this is the only possible thing we could get. And 2002 is 2 times 7 times 11 times 13. So now we're going to have what? D2 plus 11. So 13 times D4 is 14. Needs to be equal to DD5, which is D of 11. And what is D11? Well, if you go backwards, you have D16 is 2002. Then you have 2002 over 2. Just combine them with these. 2002 over 7. 2002 over 11. So this is D16, 15, 14, 13, 12, and then 11. So that doesn't make a lot of sense what I've just written down. This is D16, D15. Wait, what is D5? D5 is equal to, oh, D5 is 13. So now this is 16, 15, I forgot how to count, 14, 13. So we need to show that this is equal to, actually D13, not D11, which is equal to 2002 over 11. However, this is 2 times 7, 13, 11. They make 2002. And this shows that these numbers, which we've, for a bunch of these cases, show it has to be these numbers. We've showed that these, in fact, are numbers. And I really invited you to try out this problem. And I hope if you didn't try it out, that at least you learn something about this sort of case-by-case analysis, right? You're trying to move the problem forward until you get to a solution, which is what we have done here. We've tried this, tried that, you nudge it here, you nudge it there, and you're sort of moving and moving until you get to a solution. This finishes up our problem, and as always, thanks for problem solving.